Hey everybody, and welcome to the first of a couple of videos on alternative interpretations of probability, or I might say different kinds of probability. Thus far, we've been using the mathematics of unconditional probability to model epistemic probability, and the mathematics of conditional probability to model inductive probability. So we've been viewing probabilities as attaching either to propositions or to pairs of propositions. And we viewed these probabilities as measuring how likely a subject takes these propositions to be, either just in themselves, in the case of epistemic probability, or given some further statement as a condition or premise, in the case of inductive probability. Thus, we've been casually viewing probability then as a measure of reasonable degree of belief. This is one prominent interpretation of probability, that it is a measure of reasonable degree of belief. This makes sense given our aims in this course, where we're focused on cashing out inductive probability, or measuring the strength of inductive arguments, as we've been interested in how much a reasonable person should believe a conclusion given some set of premises. In this video, though, I want to suggest how the mathematics of probability can also be employed to model some distinct but related phenomena, right? Namely, in this video, we're going to focus on relative frequency as an interpretation of probability, and then the next video we'll look at objective chance as an interpretation of probability, and then we'll start to explore in that video and in a couple videos for next week the interrelations between these three kinds of probability. Okay, so let's start by thinking about relative frequency. Now, in the case of interpreting probability as relative frequency, rather than viewing probability as attaching to propositions, we're going to view it as attaching to properties. So let's recall what properties are. Properties are, right, what we attribute to objects in simple statements. So for example, right, if I had the simple statement, Shrek is an ogre, right, what I'm doing in that statement is I'm attributing to an entity, Shrek, the property of being an ogre, right? So here the property would be being an ogre, right? And I might denote that with a lowercase letter, maybe O in this case, right? Much the same way that we represented simple statements with lowercase letters when we were doing propositional logic, so too we can represent properties with lowercase letters. And note that just as we could combine simple statements with our logical connectives of and or not, so too we can do something analogous with properties, and we can negate properties, conjoin them with ands and ors, right? So for example, we have the property of being an ogre. We could also have not O, right? Which is the property of not being an ogre, right? Or if we have D being, say, the property of being a donkey, then we could also have, right, the property O or D, right, which would be the property of being either an ogre or a donkey, right? And so on. And corresponding to tautologies, in the case of propositional logic, in the case of properties, we have, right, universal properties that we might want to distinguish. And these are properties that a thing has to have, or that every object bears, right, just in virtue of the meanings of the terms and or not. So something like being an ogre or not being an ogre, right? Everything is either an ogre or not an ogre, right? And corresponding to contradictions, in the case of propositional logic, here we'd have what we call null properties, right? These are properties that no thing could ever bear, right, given the meanings of terms and or not. So things like O and not O, right? The property of being an ogre and also not being an ogre, right? No one could have that property, right? And just like we used truth tables to figure out which statements were tautologies or contradictions, we could use an analogous thing that we call property tables that could help us figure out what properties are universal or null or continuous. Okay, So properties are going to be what we're assigning probabilities to in the relative frequency interpretation. But we're always going to have some background domain or reference class in mind when we're doing so. Reference class, right? And this is just a set of objects, right, that constitutes sort of the population of interest for us in a given problem. A set of objects. And I'll typically represent it with like a capital letter D to represent our domain or reference class. So I'm going to assume that we have a domain or reference class of objects and that we have a set of simple properties, right? Things like being an ogre or being a donkey. And this maybe I'll represent with a capital letter Z. It's our set of simple properties. And just like in the case of propositions, where we could take a set of simple propositions and form a logical algebra generated by that set of simple propositions, we can do the same thing with properties, right? So I can let, let's say, A of Z be the algebra that's generated by Z. What does that mean? Well, it means it's going to be it's going to be a set that consists of all the simple properties that contain in Z, plus all the logically complex ones you can build out of that using and or not. So for example, right, maybe Z is a small set consisting of the property of being an ogre and the property of being a donkey. Then, right, the algebra generated by that would also have the property of being an ogre in it and the property of being a donkey. But it also have, right, the property of not being an ogre, the property of being an ogre or a donkey, and so on, right? All the properties we could build out of O and D and our logical connectives of and, or, and not. Okay, now, before we introduce the relative frequency interpretation of probability, I do need one more piece of formal setup, and that is a number of function. So I'm going to introduce this function, the number sign, and it'll be fixed to a particular domain or reference class. And it's going to be a function from an algebra of properties to the natural numbers, right? And intuitively, it's going to pick out, for any property, the number of items or objects in our reference class that bear that property. So, for example, right, the number of, say, property D might be the number of donkeys, right? The number of objects that have the property of being a donkey in, right, our domain D. So you fix a particular domain or reference class, and this number of function will tell you how many things in that reference class have a given property. Now we can define relative frequency. Right? So a relative frequency function, which I'm going to write as big F indexed to a domain D, is going to be a function from, again, an algebra of properties to, in this case, we'll say the real numbers, and we'll define it as follows, right? F D of a property X is equal to the number of items in D that have the property X over the total number of objects in D. And we could write that a couple ways. One convenient way to write it is just as the number of objects in D that have a universal property, say X or not X. Right? That'll give us the number of items in D. Right? So F is then telling us the proportion, F of any property is telling us the proportion of items in our reference class that bear that property. Okay? Now, it's fairly straightforward to show that FD, so understood, is going to be a probability function, at least if we interpret the probability axioms as being about properties, right, rather than propositions. So we could actually make that a proposition that FD behaves like a probability function. Which is to say it satisfies the probability axioms. So let's convince ourselves that this is indeed the case, right? we'd want to show that each of the axioms is always satisfied by a function like this for any reference class that we fix. Well, first would be normality, right? Remember in the case of when we were viewing probabilities attaching to propositions, we said that for a function to be a probability function, it has to assign probability 1 to any tautology. The analogous thing here would be that this f function has to assign 1 to any universal property. But that's, of course, going to be the case, right? If we took any universal property, I'll just for definiteness say maybe x or not x, right? By the definition of this relative frequency function, this is going to be equal to the number of things in D that bear that universal property over the total number of things in D, but that's just, right, the number of things that bear the universal property since everything bears it, right? So this is obviously just going to be 1 because it's a number divided by itself. So universal properties always have relative frequency 1 in any reference class. Then we could consider, right, non-negativity, right? Remember, this is the requirement that probability functions never assign anything a negative number. Well, that's going to hold in this case, right? Because the relative frequency of any property in a reference class can never be a negative number, right? It always has to be at least greater than or equal to 0. And this is since it's defined in terms of this number of function, right, that is only positive, right? It's a function that only takes on positive numbers, so we're always just dividing a positive number, or excuse me, a non-negative number by a non-negative number, since it could potentially be 0. But we're never going to get a negative number back. So since this is positive. All right. Now I should note here that I'm implicitly assuming through all this that our domain D is both finite and non-empty, right? If it was either infinite or had 0 things in it, then these ratios wouldn't really make sense. So I'm assuming we're always working with a finite domain that has something in it, right? Okay. And then the third thing we want to verify is additivity, right? So this would mean that the relative frequency of a disjunctive property, right, in which the disjuncts are incompatible with one another, that would be the corresponding analog to mutual exclusivity, is just equal to the sum of the relative frequencies of those properties taken individually, right? That is to say, right, if we have any fixed domain D, right, the relative frequency of a property x or y should be equal to the relative frequency of x in that domain plus the relative frequency of y in that domain if x and y are incompatible properties, right? And we can understand what it means to be incompatible. It means, right, two properties are incompatible just in case nothing can bear both properties, right? It couldn't be both x and y, right? But of course, right, we can sort of unpack this to see what this would mean, right? This would mean that we'd have to have the number of things that bear x or y over the total number of things in D. Maybe I'll use x or not x as my universal property. That doesn't matter. Would have to be the same as the ratio of the number of things that have x over the total number of things added to the ratio of the number of things that have property y over, again, the total number of things, which I can, again, just write as x or not x. Let me write that a little better, actually. X or not x. All right? But, right, here we see that we have a common denominator for all three of these terms in this equation. So the equation is going to be true, the equality is going to hold, just in case it holds with respect to the numerators, right? Just in case the number of things in D that have x or y is equal to the sum of the number of things that have x and the number of things that have y, right? But, right, we know that has to hold. We know that the number of things in D that are x or y has to be equal to the number of things that are x plus the number of things that are y, because x and y are incompatible properties, right? So we're not going to be double counting or anything here. We don't have to worry about that, right? The number of things that bear the property being x or y is just equal to the number of things that bear the property x plus the number of things that bear the property y. Right? So since x and y are incompatible, right? But since we know that this is true, then we know that the above claim is true, and hence that additivity is true, right? So we verified fairly straightforwardly that a relative frequency function is a probability function, which means all of the consequences that we derived about probability functions are going to hold in the case of relative frequency functions. Okay, so maybe we could think of a couple examples here of relative frequency. So maybe we do a card example. So suppose we have maybe a standard 52 card deck, and that we could view as our reference class, right? So our reference class, C, right, could be the set of all 52 cards in the deck, right? The set of 52 cards. Right? Then we could have, we could think of properties, like maybe the property of being black or red, right? Color code this. Red. These are simple properties, right? And we could think of, the relative frequency of these properties within our reference class, right? So FC of, say, black, this would be the proportion of cards in our deck that are black, right? And we know that that's 1/2, right, in a standard 52 card deck, because it's really, the number of black cards we have in the deck, which is 26, over the total number, which is 52. But of course, that's just 1/2, right? We could introduce more complex, property spaces, like properties of being a heart, right? Maybe we'll do that. Let's see. So we'll consider here the property of being a heart. And we could ask, what is the relative frequency of being a heart in the deck? So being a heart. Well, this would be equal to the number of hearts over the total number of cards in the deck. We know there are 13 hearts in the deck over 52. So the relative frequency of heart in the deck is 1/4. Now it's intuitive from this example that there's going to end up being a sort of connection between probability interpreted as reasonable degree of belief and probability interpreted as relative frequency, right? If we're drawing cards from the deck, at least if the deck is well shuffled, our degree of belief that cards with certain properties are going to be drawn from the deck is going to be equivalent to or related to the relative frequency of those properties within the deck, right? And that connection between relative frequency and reasonable degree of belief is something that we'll explore more next week. But in the next video, we first want to look at another interpretation of probability, the interpretation of probability as objective chance. So we'll do that in the next video. Please remember to complete the participation poll for this video, and I'll see you guys next time. All right, thanks.